Let's talk about alternating series. So this picks up right where we left off in the notes, and it's just more notes instead of the reading this time. So what I have here is just a recap of the alternating series test. This test is for alternating series. So alternating series are the kind that go plus minus perfectly. So they can be written as -1 to the n times an. So in that case, when we write it that way, the an is positive, and it's just representing the magnitude of the terms. And then this -1 to the n, depending on how the index is used, and you can see this first example that we're going to do here, depending on the example, that n might be something slightly different. So in this case, it's n plus 1. It could be n plus 5. Those kinds of things don't really affect this theorem, so you don't have to worry about rearranging. So we'll just say, or n plus 1, and of course that n could also be a k. We use both of those letters frequently. Okay, so you start with an alternating series that is in this format or something very similar, and you want to decide whether it converges or diverges. That's always the question that we're answering for this chapter so far. So the alternating series test says if the limit of the magnitude of the terms, so the an piece, if that limit is 0, then your series converges. It's actually our simplest theorem, I think, at least in a long time, which means that it's actually really easy for an alternating series to converge, because instead of just adding, you're adding and then subtracting a little, and then adding and subtracting a little. So that like constant subtraction is what kind of keeps the sum in check. So it's a much lower bar for these things to converge. So I also want to point out here kind of the implied other situations here. So the other possibility is that this limit is not 0. So if you start with an alternating series, you go to compute that limit and you get something other than 0, either it doesn't exist or it equals some other number, look to the nth term test. So this is the scenario here where technically the alternating series test is inconclusive, right? The only conclusion is if this, then that. So if that's not true, this test just isn't giving you any information. But if that's true, the nth term test is probably what's going to save the day. So this was one of the very first tests that we had, and it said if the terms of your series don't go to 0, then your series diverges. So if this is the case, you do have to throw the -1 to the n back in and consider like the limit of the entire formula for the terms. But if that limit's not 0, the whole thing's limit isn't 0, and your series is going to diverge by the nth term test. Okay, so what I have prepared here is 2 different examples just to add on to what we did in class. Okay, so the first one here is the sum from n equals 0 to infinity of -1 to the n plus 1 over n factorial. I'll remind you, 0 factorial is defined to be 1, so this is actually okay to start at 0. And this is a nice example of we have n plus 1 instead of an n here, but this theorem will work the same way. I'm not going to bother changing this format. What I am going to do is take a moment and consider what my an is. And I would say in this case, it's 1 over n factorial, right? So sort of what I'm doing is taking this -1 to the power and kind of bringing it out front. So it's just a 1 up here. This is the magnitude of all the terms, and then this is just creating plus minus. So it's the limit of these things that we want to consider. So the limit as n approaches infinity of 1 over n factorial. Even without the factorial, this limit would be 0. N factorial gets really, really big really fast. So I'm going to say that limit equals 0 for sure. So that tells me that this series I started with is convergent. Okay, so I have one more example. So here we're using k as the letter instead of n. So we're going to do the limit as k approaches infinity, but it all works the same way. We're just swapping out the letter. And this one you can see my an, I'm going to call an ak because k is the letter, is going to be this magnitude here, because this one's kind of perfectly arranged like what we have in the test here, -1 to the power with a formula, -1 to a power with a formula. Okay, so I want the limit of this stuff. So now we have the limit as k approaches infinity. It's k squared plus k over 3k squared plus 1. Okay, so this is one of those limits where there's at least two ways to get to the same answer here for this limit. One thing you could do is notice that this is a rational function, meaning there's a polynomial on top and the bottom, so all we need to do is look at the ratio of our leading terms. That gives us a 1 over 3, and that's our answer. You could also realize this is infinity over infinity and use L'Hopital's rule. That would also bring you to 1/3. So whichever way you feel most competent and comfortable with is what you should be using for these limits. The most important thing is that you're comfortable with your answer. Okay, so what we get here is 1/3. And we say, wait, what does that mean for this test, right? So whether this is the limit comparison test or the ratio test, a 1/3 could mean all kinds of things. So what we were looking for was for that limit to be 0, we would have a conclusion. So we are kind of in this red note here. Our limit was not 0. So technically the alternating series test is inconclusive. But this is a big hint that we should look to the nth term test. Because our best guess at this point is that this series is divergent, and the nth term test can probably get us there. So for the nth term test, we want to consider the limit as k approaches infinity of the entire formula that creates these terms. Now, this is a lot more intimidating when you look at it all together, but essentially what's happening, because the magnitude is going to 1/3, is that half of these numbers, kind of every other number, is headed towards 1/3, and then the other half, so the other every other numbers, are headed towards -1/3. So some are going to 1/3, and then the others are headed to -1/3. Which says that the limit of all of this does not exist, right? Because you kind of have that like split situation here. Okay, so the nth term test says if that limit isn't 0, which is what we have here, then your series diverges. So we'll conclude diverge by the nth term test. Okay, so that's our last example for the alternating series test. From here, we're going to get a little bit of vocab. All right, so we have a definition. And this will be for conditional versus absolute convergence. You know what? Instead of having -1 to the power, I'm going to use my handy dandy little thingy here. Look at that. Here's what I'm going to do. I'm going to write my series here, and I'm using Bn here because I don't want you to confuse it with the An or the Ak from an alternating series where you're pulling out the magnitude. Bn represents the entire formula for the term. Okay, so let's say you have this series and it converges, and we're sort of assuming that this is an alternating series, or some sort of series that has positive and negative terms. So it may not be actually alternating, it may just be kind of like more erratically positive and negative. So pos and neg terms, and you'll see why we need that in a minute, because otherwise this just won't make sense. So there are two scenarios here. Okay, so we'll say one possibility is that it converges absolutely. That's our vocab word, converges absolutely, if the series of the absolute value of those terms, so you essentially ignore the plus minus business, if that also converges. Okay, and then the alternative to this is that this diverges, but this is convergent. So we'll say the alternative is that it converges conditionally if the series of the absolute value terms diverges. Okay, so if the BNs are all positive, then it's just convergent and definitely absolutely convergent, because this and this would be the same thing. So this is really only interesting when this series has both positive and negative terms, which usually means it's alternating, but we'll see in class there's at least one type where it has all of this going on, but it's technically not alternating. Okay, so if you have, let's say, an alternating series and it converges, usually you're asked not just to decide whether it converges, but if it converges, decide if it's absolute convergence or conditional convergence. And we'll do just a couple of simple examples here to practice these vocab words. So we'll keep that definition with us and move on to another page. Let's consider the alternating harmonic series. Sometimes we see this with -1 to the k plus 1. Here we're using -1 to the k. Still kind of the same idea, they just start on different signs. So this one, your AK terms are 1 over k. So if we consider the limit of those terms as k goes to infinity, we sure enough get 0. So we can conclude that this series, the alternating harmonic series, is convergent. Now, let's say we also need to decide whether it converges absolutely or it converges conditionally. So we want to decide, is that convergence conditional or absolute? So we have a secondary question to answer now. So that means that we need to consider the absolute value version of this series. So the absolute value of -1 to the k times 1 over k. So those absolute value symbols are just stripping away the minus sign that is on every other term. So what's going to come out is just the regular harmonic series, right? It's just those powers of -1 don't mean anything anymore because they're getting absolute valued and going away. So here we just have the regular harmonic series, which we know is divergent by using the p-test or the integral test, but this is one that we've decided previously is divergent. So because we got divergent for this other version of the series, we would say this convergence is conditional, so it converges conditionally. If we had gotten convergent here, we would have said this convergence was absolute. Let's see one more example before we finish this video of deciding, here's an alternating series, is it convergent or divergent? So this is the question we're answering. Is it convergent or divergent? If it's convergent, is it absolute or conditional? For an alternating series, it would always be one of those two types of convergent if it is convergent. Okay, so let's use another fairly simple example. Let's say -1 to the k plus 1 times 1 over k squared. 1 to infinity. This is really similar to the last example except for the k squared in the denominator. My AK will be 1 over k squared. The limit of that as k approaches infinity is definitely 0. So by the alternating series test, we conclude that this series converges. Okay, so now we're going to answer this second piece here. If it's convergent, is it absolute or conditional? So now we want to consider the absolute value version of this series. And just like the previous example, all the absolute values are doing are essentially making this -1 powers business just obsolete, right? Because every time it gets absolute value, it goes positive anyways. So without the powers of -1, this is just the series of 1 over k squared. And this example is especially nice that we can just kind of look at this and answer. Using the p-test, we can tell that this is convergent. So that tells us that the convergence of our original series was absolute, right? It converges with or without the plus-minus situation here. So this one, we would say this converges absolutely. Whereas the previous one only converged conditionally because the absolute value version was divergent.